Channels are Go's preferred way to communicate between goroutines. But sometimes you just need shared memory, a counter that many goroutines increment, a cache that many goroutines read, a connection pool that needs to be initialized exactly once. That's what the sync package is for. This episode covers every primitive in the package, WaitGroup, Mutex, RWMutex, once, and atomic, when to use each, and the pitfalls that trip up even experienced Go developers. You've already seen WaitGroup used in worker pools and pipelines. Now let's understand exactly how it works. A WaitGroup maintains an internal counter. Add n, increments it by n. Done, decrements it by 1. Wait, blocks until the counter reaches 0. 3 rules that matter. First, call add before launching the goroutine, not inside it. If you call add inside the goroutine, the main goroutine might reach wait before the goroutine increments the counter, and wait returns early. Second, always call done via defer. This guarantees the counter is decrement even if the goroutine panics, preventing wait from blocking forever. Third, always pass a pointer to WaitGroup. Passing by value copies the counter, and the goroutine's done decrements a different copy from the one wait is watching. The canonical pattern is the same every time. Declare the WaitGroup, loop, call add 1, before go, launch the goroutine with deferred WG. Done, as the first statement, then call wait after the loop. A race condition is when 2 goroutines read, modify, and write the same variable concurrently. The increment operator counter ++ is actually 3 operations. Read the current value, add 1, write it back. If 2 goroutines do this simultaneously, both might read the same value, both add 1, and the final count is 1 less than expected. Run this 100 times and you'll get 100 different answers. A Mutex mutual exclusion lock solves this. Lock acquires the lock. If another goroutine holds it, the caller blocks. Unlock releases it. Only one goroutine can be between lock and unlock at any moment. That's the critical section. Always unlock with defer. Without defer, if your function has multiple return paths, an early return on error, a panic, you need to manually place unlock before each return. Miss one and you have a permanent deadlock. With defer mu, unlock, immediately after mu, lock, you can never miss it. Go ships a built-in race detector. Run Go run race or Go test race and the runtime instrument's memory accesses to detect concurrent reads and writes. Catches races that don't crash but produce wrong results. Use it in CI, it has no false positives and finds real bugs. A regular mutex allows only one goroutine inside at a time, even for reads. If you have a cache that 10 goroutines read constantly and rarely write, a mutex serializes all those reads unnecessarily. RWMutex has 2 lock modes. RLock and RUnlock are for readers. Any number of goroutines can hold an RLock simultaneously. Lock and unlock are for writers. Exclusive access blocks all readers and other writers. A write waits until all current readers release, acquires exclusive access, writes, then releases, allowing readers to proceed again. The safe cache struct is the canonical example. The struct embeds an RWMutex alongside the map. The get method calls RLock. Many goroutines can read concurrently. The set method calls lock, exclusive. This pattern makes any map thread safe with minimal code. When to use RWMutex versus plain mutex. Use RWMutex when reads are significantly more frequent than writes and read operations take meaningful time. For very short critical sections, a single increment, a plain mutex has lower overhead than RWMutex. For caches, configuration stores, and data that's set once and read thousands of times, RWMutex pays for itself. Sync. Once solves one specific problem. Running an initialization function exactly once even when multiple goroutines trigger it simultaneously. The naive approach, a Boolean flag plus a mutex, works but is verbose. You need the mutex, the Boolean, the lock, the check, the init, the set, the unlock. Get any step wrong and you either initialize twice or deadlock. Once.do takes a function and executes it exactly once, no matter how many goroutines called do concurrently. The first caller executes the function. All others block until it completes, then return. They don't rerun the function. After the first call, every subsequent do is a no-op. The canonical use is lazy initialization of expensive resources, loading config from disk, establishing a database connection pool, setting up a logger. Wrap the initialization in a function, pass it to once.do, and any goroutine that needs the resource calls getConfig. The first call initializes it, every subsequent call just returns it. One important restriction: if the function passed to do panics, once considers it done, future calls to do won't rerun it. So the initialized state may be invalid after a panic. Handle errors inside the function or store the error alongside the initialized value. The sync/atomic package provides CPU-level atomic operations, reads, writes, and increments that execute as a single uninterruptible instruction, with no lock involved. They're faster than mutexes for single variable operations because there's no OS-level blocking, no context switching, just a hardware guarantee. Add int 64 increments atomically. Load int 64 reads atomically, important on 32-bit systems where a 64-bit integer read isn't naturally atomic. Store int 64 writes atomically. Compare and swap reads the current value, checks if it equals the expected value, and only then writes the new value. This is the foundation of lock-free algorithms. Atomic value lets you atomically swap any value. Store a new value, and any goroutine loading at that instant gets a complete, consistent value, never a partially written struct. This is ideal for hot swappable configuration. A background goroutine periodically fetches new config and stores it. Request handlers load it on every request. No locks, no blocking. Use atomic for performance critical counters, single Boolean flags, read mostly configuration that needs atomicity. Don't use atomic when you need to coordinate multiple variables together. That's what Mutex is for. RWMutex is a higher-level wrapper from golang.org/x/sync that combines WaitGroup with automatic error handling. The problem it solves: when you have n concurrent tasks and any might fail, the WaitGroup approach requires an error channel, a goroutine to close it, and manual collection. 3 constructs for one idea. RWMutex replaces all of that with g.go and g.wait. Call g.go with a function that returns an error. RWMutex launches it as a goroutine and tracks the error. Call g.wait when you're done launching. It waits for all goroutines to finish and returns the first non-nil error any of them returned. Clean and readable. RWMutex with context adds cancellation. It returns an RWMutex and a derived context. When any goroutine returns an error, RWMutex automatically cancels that context. Pass the context to every goroutine and check CTX. Done. When one task fails, all others stop early. This fail-fast behavior is usually exactly what you want. If one of 5 API calls fails, there's no point waiting for the other 4. The 2 most dangerous sync bugs are race conditions and deadlocks. Race conditions are silent. The program keeps running but produces wrong answers. Always run go test race in CI. It instruments every memory access and reports data races with a full stack trace. No false positives. Deadlocks make the program hang. The most common cause with mutexes is inconsistent lock ordering. Goroutine A locks mutex 1, then mutex 2. Goroutine B locks mutex 2, then mutex 1. They each hold one lock and wait for the other forever. The fix: always acquire multiple locks in the same order, everywhere in your codebase. 2 other common mistakes. Never hold a mutex across a channel operation that might block. You can deadlock the entire program. And never copy a mutex, WaitGroup, or once after first use. Their internal state becomes inconsistent. If you need to pass them around, pass pointers. The decision guide is simple. Communication between goroutines, use a channel. Protecting shared state with multiple fields. Mutex or RWMutex. One time init, once. Single hot counter, atomic. Concurrent tasks with error handling RWMutex. WaitGroup waits for goroutines, add before go, done with defer, pass by pointer. Mutex protects critical sections, always defer unlock, detect races with go race. RWMutex allows concurrent readers when writes are rare. Once runs initialization exactly once regardless of goroutine count. Atomic provides lock-free operations for single variables and hotswap for values. RWMutex is WaitGroup plus error handling plus context cancellation. The meta rule: prefer channels for communication, sync primitives for shared state, and always test with the race detector. It's built in and it's free. Next episode: generics, type parameters and constraints, the most significant language addition since Go 1.0. This course is based on the complete guide to Go programming, available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 17.